Hello friends, I am Amir Nizami and today we are going to study the Matlab code for forced vibrations of a viscous damped single degree of freedom system. So let's start. So first of all we will see the basic equations and then we will have the Matlab code for that. So let's start with the basic equations, and that is mu double dot plus cu dot plus k of u is equals to p of t, where P of T is the external force applied, external force or applied force or force applied. This external force applied may be harmonic, it may be non-harmonic, harmonic, it may be periodic, or it can be aperiodic. So external force may be any kind of applied force which is the function of time. So we are having a simple case here. So we will just see for a simple case mu double dot plus cu dot plus k of u is equals to f naught sine of omega t. We are having a harmonic case we are considering, where sine of omega t forcing function. So we can write it as if we will divide with respect to m on both sides. So we can write it u double dot plus c by m u dot plus k by m into u is equals to f naught by m into sine of omega t. So we can write it again u double dot plus c by m was 2 xi omega n, we have already seen it before in the last two lectures, plus k by m was omega n square into u is equals to f naught by m into sine of omega t. Now here this is omega, this omega is called the forcing frequency, forcing, or it is also called driving frequency or external frequency, which is the frequency provided by external loading. And here we have shown here omega n which is natural frequency. So we should know omega n is the natural frequency which is inherent of a single degree of freedom system or any structure, because its own stiffness and mass is there. So therefore natural frequency is the inherent property of a body or any structure. And omega here which we have written sine of omega t, that is the external frequency, we can say forcing frequency or driving frequency, okay. So we should note one point here, note that we do not want to make omega should be equals to omega n. It should not be such a case. If omega is equals to omega n, means applied frequency is equals to the natural frequency, then what will happen? Resonance will occur. Resonance will occur. So theoretically we say if there is no damping, then infinite amplitude will take place. But due to damping, a frequency increases a lot. But even though due to damping, it is some finite value only. So we don't want that at any point the forcing frequency and the natural frequency matches. If it will match, then the resonance will occur where a large amplitude would be there. So this must be very clear to us, because most of the time we don't understand that what is the omega and what is the omega n. So we must take care that omega n we are specifically writing for the natural frequency, and omega here we are writing for the forcing or driving frequency. It is the externally applied load where we have provided this frequency. Okay, so now we can write this as u dot plus 2 xi omega n into u dot plus omega n square of u equals to 1 upon y into sine of omega t. So what is y here? So y we are writing as m by f naught. If you will write it 1 upon m by f naught, then it will again cover f naught by m. So we have written in this manner. So it would be equals to y of u double dot plus 2 xi omega n into y of u dot plus omega n square y of u is equals to sine of omega t. Now we know that this equation is a second order differential equations, and we can solve it. And when we solve, let us have this equation 1. So our response, our total response would be u homogeneous solution plus u particular solution. Means homogeneous solution what? That first solution would be that this equation this much would be equals to 0, and we have considered it in the last case. We have studied how we do that. And in the second case, particular solution would be there, so the right hand side is sine omega t, so we will solve accordingly. Okay, so now we will write it again, the equation yu double dot plus 2 xi omega n y of u dot plus omega n square y of u equals to sine of omega t. So now if we will differentiate it, if we want the solution, so let us consider that u particular, because for the homogeneous case we have studied that right hand side we will equal to 0, and then we will solve this equation and we will get from there. So we can say that for u homogeneous case we will write y would take common, and we will see that u double dot plus 2 xi omega n u dot plus omega n square of u would equals to 0, and then we will solve for the homogeneous solution, so we will get that value. But now for the right hand side is non-zero, so we will another case we will consider that particular solution, and we can write it as u of p is equals to m of sine omega t plus cos of n times cos of omega t. And if you will differentiate it, so up dot would be equals to m omega cos omega t minus n omega sine omega t. If you will again differentiate it, second time differentiation, then m omega square with minus sine of omega t minus n omega square cos of omega t. So let us consider this equation as 2 and this equation as 1. So we will substitute equation 2 in equation 1. So we'll put it here. So y into u double dot is minus m omega square sine omega t minus n omega square cos of omega t plus 2 xi omega n y into u dot, and u dot is m omega cos of omega t minus n omega sine of omega t plus omega n square into y of u, and u is m sine omega t plus n cos omega t equals to sine of omega t, means here right hand side is 1 into sine of omega t, plus we can also write it as 0 into cos of omega t. So why we have written in this manner? So that we can compare the sine and cosine coefficients on both sides, so so that we can easily find out the values from here. So if you will just solve it, so we will get n is equals to minus 2 xi omega n into omega upon omega n square minus omega square into m. So finally we will get, and we will solve m and n, so we can write it directly that what would be our value finally. So it would be equals to so we will write the final value. So let us write n is equals to minus 2 xi omega n omega upon y into omega n square minus omega square plus 2 xi omega n into omega whole square, and m would be equals to omega n square minus omega square upon y into omega n square minus omega square whole square plus 2 xi omega n omega whole square. Okay, and here it's also whole square. So n and m we have found, and y we know that it is m by f. Okay, so now we can also write it as minus, if you will differentiate this value with respect to omega n, so we can get, so we will write it in the first, let's write the equation. If you will substitute m and n in up, so we will get the solution as up would be equals to omega n square minus omega square f naught by m upon omega n square minus omega square whole square plus 2 xi omega n omega whole square into sine of omega t plus minus 2 xi omega n omega f naught by m upon same value omega n square minus omega square whole square plus 2 xi omega n omega whole square into cos of omega t. So now if you will write u of p is equals to 1 minus, we have considered eta as omega by omega n. Okay, so we can write it as 1 minus eta square into f naught upon, because we are just differentiating with omega n square, the last equation, so it would be k equals to m omega n square, so it would become f naught by k upon 1 minus eta square whole square plus 2 xi eta whole square into sine of omega t plus minus of 2 xi eta f naught by k upon 1 minus eta square whole square plus 2 xi eta whole square into cos of omega t. So it is our particular solution, and now we know that the total solution u would be equals to u particular plus u homogeneous solution, and homogeneous solution depends on cases. That case 1 was that depend on zeta, we can say, so zeta was greater than 0 and less than 1, so our solution was u homogeneous was equal e to the power minus xi omega n into t u naught cos of omega dt plus u naught dot plus xi omega n u naught upon omega d into sine omega dt for the case 1. Case 2, when xi is equals to 1, that is critical damped, so we can write homogeneous solution for this is equals to e to the power minus xi omega nt u naught into 1 plus omega nt plus u naught dot into t. And the third case, case 3, would be xi is greater than 1, that is overdamped case, and we have u of h is equal to e to the power minus xi omega nt u naught cos of hyperbolic omega star t plus u naught dot plus xi omega n u naught upon omega star into sine of hyperbolic omega star t. So it is cos hyperbolic and sine hyperbolic value. So these are the three cases. So respectively, if the case is depends on xi value, so our total solution would be equals to u particular plus u hyper u particular plus u homogeneous. And now we will see the solutions. So suppose if xi is considered as 0.02, so what it is, it lies between 0 and 1, so it is underdamped case. Underdamped case. So we can write the total solution as U homogeneous plus U particular, and we know U homogeneous cases that what is the value for this. So e to the power minus xi omega n t u naught cos omega dt plus u naught dot plus xi omega n u naught upon omega d into sine of omega dt plus u particular, and particular solution we have right now solved up here, which is 1 minus eta square. So we can also write here the particular solution, and it is 1 minus eta square f naught by k upon 1 minus eta square whole square plus 2 xi eta whole square into sine of omega t plus minus 2 xi eta into f naught by k upon 1 minus eta square whole square plus 2 xi eta whole square into cos of omega t. So it is our total solution. This part was homogeneous and this part was particular solution. So complete solution would be the sum of both. So in MATLAB we will code. So first we will solve for homogeneous part. So u of homogeneous we will solve, and then we will solve for particular case, and then we will write the total response as uh plus up. So let's go to the MATLAB. So we will go to MATLAB. So first we will clear all. Okay, so the solution for mu double dot plus cu dot plus ku equals to f naught sine of omega ft. So for the homogeneous case, we know that this would be equals to 0 right hand side. So we have solved for the right hand side for 0 first, homogeneous case, and then we will solve for the right hand side as forcing function. So here we have denoted the forcing frequency with omega f. Okay, and for the natural frequency with omega n as the natural frequency. Okay, xi value it will ask from us that whether it is xi is between 0 to 1, so we can put that value greater than 1, or xi is exactly 1. So we will have the command xi equals to input, enter the value of xi. Similarly, it will ask for f naught, which is the external force coefficient. So f naught would be the value we will provide, mass m value it will ask, and the time period of the structure it will ask for that. So omega n we know natural frequency, which is 2 pi by time period, that is capital T. K is the stiffness, we know that it is m into omega n square. So it is here we have written. Omega f is the forcing frequency, so we have also written this. And omega st, omega star, which is omega n into square root of xi square minus 1. And the initial conditions are already given, that u at t equals to 0, u naught equals to 1, and v at t equals to 0 is 1. V here we have written for u dot naught, means u dot is the velocity, which is here velocity. So in the vector format, because it will store in the displacement value, So we will write u of 1 equals to u naught and v of 1 equals to v naught. Now eta, we have just considered that the forcing frequency omega f by omega n, and we have just, for our simplification, we have just taken a constant a equals to 1 minus eta square for just writing the formula in a short way, and b is 2 into xi into eta, and f naught underscore k is f naught by k, and we have taken the duration up to 16 seconds and we have discretized it with 0.02, and omega d we have considered as omega n square root 1 minus xi square, and this square root is, in the short we can write sq equals to this much, and we know that we will find the homogeneous solution. So we are having a, we will store in a matrix form or a vector format, so we have zeros of length of t, comma 1, up is the particular solution and it is the total solution. So we have just written it so that the value would get stored in it. So for I equals to 1 is to length of t, ep exponential value, we know that exp into minus xi omega n into t, and t we have already discretized here. T means duration, that 0 to 16 seconds with a discretized time delta t equals to 0.02, so that we are taking the loop here, that it will varying from t will get varied, and corresponding to t our value of u and uh and up will vary. So here t of I, so I here is the variation. So we have considered Si is sine of omega dt and Co is cos of omega dt. Sine underscore h is sine hyperbolic and cos underscore is cos hyperbolic. Omega star, omega st is the omega star value. Now we will have a constant coefficients here. So up1 constant, we have solved it. up2 constant, we have considered it, and then we have considered the 4 case. So the case 1 is underdamped if xi is greater than 0 and xi is less than 1. So our homogeneous solution would be this. And case 2 is critically damped, xi equal to 1. Then our homogeneous solution would be this. And if xi is greater than 1, overdamped, then our cases would be this homogeneous solution. And if it is undamped, means there is no xi, so our solution would be this. So we have already changed u of h, we have written homogeneous case, and particular solution we know that it is the direct, we have written the values of u of p. Okay, so our u of t would be equals to up plus uh, and then it would get end, and we will just plot the figure for homogeneous solution, particular solution, and the total solutions. Okay, ut. So let's see, we will run this code. So it is asking for the xi value. So first one, we will take the underdamped case, means 0 0.02 or 0.3, any value between 0 and 1 we have considered. Let's, and if it is asking for the static forces, so let's apply 5 is the static force now. So let's see, it is showing the 3 figure. So figure 1 is homogeneous solution. So we can see that with respect to time it is getting decaying, and then it is the up, the particular solution, with respect to time there is no changes. Okay, so it is the particular solution, and we can see here that the total solution is the sum of both homogeneous and particular solution. So our solution is, total solution is this. In this manner it will fluctuate. So it was our underdamped cases. Now we will see again for the critically damped, means xi equals to 1. So we will run. So f naught is 5 also. So now we will see three cases. So let's first see homogeneous solution, where this is the value for at 1 critically damped. So it would show in this manner that at critically damped the vibration oscillation just gets ceased. So we can see there is no further oscillation and it becomes 0. And then the second case we can see here, the particular solution which is independent of time, so it is continuous, no effect with time. And the final solution we can see the sum of the both value, so it is shown that total solution is u homogeneous plus u particular. So we have also seen the critically damped. Now we will see for the third case, and that case is overdamped. So xi must be equals to greater than 1, so that is 2 we have considered. It was 5 we are telling. Let's see. So we can see here, so it is the overdamped case. So after 2 seconds it's got ceased for the oscillation, so it is our homogeneous solution. And then again it is a particular solution whose vibration is continuous and it is independent of means it do not get diminished with time, so it is constant with time. And then the total solution is sum of both, and we can see here. So all three cases were there, and one case we can make further also, that if there is no damping means xi is 0, no damped case. So we can see from here what will happen. U homogeneous solution would be continuously oscillate, means it would not get diminished with time, and U particular solution would be like this, and the total solution would be sum of both the values. So we have seen all the four cases. So thank you.